asks you to do the average value of a function, which is what we're learning the first day next unit. Now, you probably saw by looking at the answer key that it was the same thing over and over and over again. So when we are trying to find the average value of a function, let's see if
how I do this. I keep my things on the angle.
okay. When you're trying to find the average value of a function, here they ask us to find the average temperature. So the function we're working with is the temperature function. The average value of a function is simply the integral from a to b of our function multiplied by 1 over b minus a. So you'll see that as you look through the key, it was the same concept over and over again. This is what average value does for us. Now again, they're asking for the average temperature, which means the function that we're using is going to be our temperature function. We integrate our temperature function, it says over the first hour, so since it's measured in minutes, and that's why we went from 0 to 60. Alright, so the setup for this would simply be 1 over 60 minus 0, from 0 to 60, of 7b plus 1430, e to the negative 0.2t, and then use your calculator for that. Questions on that? Okay. So let's take a look at the other ones. 22. Go ahead and turn to 22. Yes, Morgan. Yeah, so over in the tub there, check day.
You say 22?
5, 6, or 7. Yes, 22, sorry. So again, you can see here at 14, it was from 0 to 60 of our temperature function times 1 over 60 minus 0. All right, so with 22, again, it asks for the average value, and they want the average value of this function, so we're integrating that function. Okay. We are integrating this function, and we're going from 1 to 4. So again, we go from 1 to 4. Alright, we'll just do it off a second. So again, I'm going from 1 to 4 of my function, which is e to the square root of x over 2 root x dx, 1 over 4 minus 1. Which is why we have that 1/3 times our integral. Alright, so if we look similarly with number 26, again, it says the average value, so we integrate our e to the x function because we want the value of this function, so I'm integrating this function on the interval from -2 to 2, so from -2 to 2, 1 over 2 minus -2 gives us that 1/4. Now 27 is just a little bit different in that it asks for the average rate of leakage of oil. It's still asking for the average value, but the function we're working with is our rate. And our function is 500 e to the negative 0.4t. So that is my rate function. That is what I'm integrating. And once again, it's 1 over b minus a times the integral of that function. So we will do more with that next unit, but that's really all the average value is. Questions with that? Okay. So now go ahead and take a few moments and write up on the board questions you have and put time marks next to it. We'll tackle the ones with the most time marks and then go from there. Oh. Alright, so turn in your packet to 21. Is that the one with the limit? The graph. Okay. Alright, number 21. So they say the equation for the line that's tangent to the curve and passes through the origin is what? Now be careful, it is tangent at some point, but also passes to the origin. Does e to the 2x go through my origin? No, so this cannot be the point at which it is tangent. The origin does not fall on my graph itself, so it cannot be the point at which it's passing, or the point at which it's tangent. So this, as they showed in the picture here, is our point at which it's tangent. We need to figure out what that value is before we can find the derivative at that point. So we know the equation of the tangent line. We need the point, and we need the slope. We don't know our point, and we don't know our slope. Now, in order to find our slope, typically we do our derivative. So the derivative of e to the 2x will give us what? 2e to the 2x. And then next, I would go ahead and take my derivative at that point in question. But I don't know what that is. Okay, so let's think about what else we can do. So you gotta ask yourself, well, gee, why did they tell us it went through the origin? Now, the slope of this line is going to be the slope, or sorry, the derivative at that point. But we can also find the slope by using the slope for 2 points. So again, I don't know what this point is, but I know that it's some x value and then some y value, and y is just e to the 2x. All right, so when I do my normal algebra 1 slope, if it passes through that point in the origin, then y minus y over x minus x means that my slope is also represented by the equation e to the 2x over x. Alright, so what we really have are 2 equations that represent the slope. I know this represents my slope, and this represents my slope. If they represent the same value, then we can take those and set them equal. They should equal the same slope. Alright, so when I do that, 2e to the 2x equals e to the 2x over x. Cross multiply, and I get 2e to the 2x times x equals e to the 2x. Questions so far with what I've done there? Okay. So now we just need to solve for x. Once again, in general, we should not divide by a function. So if I divided both sides by e to the 2x, that's typically not a good idea because you don't know if they're divided by 0 or not. But since we do know e to the 2x is always positive, then we won't have any issues with violating that rule of dividing by 0. But just to play it safe, I'm going to go ahead and subtract it over. Equals 0. And if I want to find what this equals 0, go ahead and factor out any common factors. So e to the 2x, leaves us with 2x minus 1 equals 0. I know that e to the 2x never equals 0 because it's always positive. 2x minus 1 equal to 0 gives us an x value of 1/2. Questions on that? Okay, so we had to use our algebra 1 slope and our calculus slope to find 2 equations, set them equal, and solve for that x value. So now I know that the x value is 1/2. How do I find my y value? Yeah, just put it in. Am I putting it into my derivative or into my original to find the y value? The original. I will need to put my derivative for the slope, but to find my y value for the point, I'm just going to put it into my original. So we have then at 1/2, the e to the 2 times 1/2, which is just e. Are we good with that? Okay. So my point is 1/2 comma e. Okay, so now we have our point. I can fill those pieces in. Now I need to find my slope. Again, we do our derivative, and now we have to find our derivative at that point of 1/2. So putting 1/2 in, I get 2e to the 2 times 1/2, which is just 2e. Alright, now our answer choices are not in that point slope form. So if I were to go ahead and distribute, I have y minus e equals 2e times x minus 1. No, minus e. 2e times 1/2 of e. Questions with that? So I have y minus e, and then here I'm just distributing, so 2e times x Negative 1/2 times 2e would be negative. Alright, so now if I go and add my e to both sides, we have that those cancel, and I get just y equals 2ex. Questions on that? We've had a couple problems like this earlier in the year when we were first dealing with our tangent line. But keep in mind, derivative tells me the slope of that tangent line, but if I know another point that it goes through, I can also use algebra 1 to find the slope of the tangent line. Alright, let's take a look at 29 next. Alright, so 29, they give us an absolute value function here. But it's not just absolute value of x, it's absolute value of natural log of x. So you can kind of think of this in terms of our graph. I know my natural log graph goes through the point 1, 0. If I were to take the absolute value of that, what would change about my graph? The negative piece here would get flipped up to be positive. So really, it would look something like that. Do we agree with that? Okay. So when they ask for the derivative, we're thinking of slope. So at least looking at this, I can know that if this is 0.1, then 1/2. The slope is going to be negative. Do you guys agree with that? Okay. So I can at least, with just thinking of our graph, eliminate c through e. Now from here, you can probably figure out that it's more likely to be negative 2 than negative 1/2. But let's take a look at it algebraically. So our absolute values, remember, we can rewrite as a piecewise function. This is your guys' Okay, so we can think of this as an absolute, or sorry, as a piecewise function. Absolute values can be rewritten, it's opposite of the function, and then the positive of the function. Now we have to figure out at what x value this is true for. Alright, so if we again think of our natural log graph, for what part of this is my graph negative? 0 to 1, and notice that we do not include, well, either of those. And then, do you guys agree that 1 on, we have that it's positive, so and really you can put the or equal to for either part of the one, but are we good with this piece? Questions on that, myself? Why do we have to do that? So absolute value, we know that we can break it up into piecewise, and I can do my derivative, and I'll have the actual derivative function to plug into there. At this point, though, by just thinking of your graph, you could probably guess that it's negative 2 instead of negative 1/2. So. Other questions so far? Okay. So again, the only way we can take the derivative of an absolute value is to break it up into the piecewise, which is why we're doing that here. So now when I go to do my derivative, just take the derivative of each piece. So negative natural log of x, the derivative is negative 1 over x, and derivative natural log of x is 1 over x. So we have from 0 to 1. Would I include 1 on either of these? Why? Yeah, right here we have that it's a cusp, which means there's going to be no derivative there. Okay. So now, when we go to do our derivative of x equal to 1/2, which piece am I going to use, top or bottom? Does 1/2 fall within this interval or this interval? The first one here. So I have negative 1 over 1/2, which gives me negative 2. So again, you could reason through this thinking of the graph and the slope of it, or look at it algebraically with their pieces. Questions on that? 15 looks like it's next. Ah, yes, 15. The first part, not so bad. The algebraic manipulation, a little rough. Okay, we're gonna need some more room here. Okay. Alright, so for number 15, again, the setup's not bad. It's getting it to these answer choices that's a little rough. But it's just algebraic manipulation, right, Logan? Mm-hmm. Good, put that away. Alright, so it says f of x plus 2 minus f of x minus 2. So I'm going to go ahead and find each of those. So f of x plus 2 would be 2 to the x plus 2. I'm just replacing my x's with that. F of x minus 2 would just be 2 to the x minus 2. Once again, I'm just replacing my x's. So when I put this together, I would have f of x plus 2 is 2 to the, here, I'll just rewrite that. F of x plus 2 minus f of x minus 2. So this is 2 to the x plus 2 minus 2 to the x minus 2. Questions on that? Now, of course, that is not one of our answer choices here. So what that means is we've got to simplify and manipulate. If I am adding in the exponents, what did that mean I did with my bases? I was multiplying. So this is the same thing as 2 to the x times 2 squared. And if I was subtracting in my exponents, what did I do with my bases? Divide. So this is 2 to the x over 2 squared. Questions with that? Now again, that is not one of our answer choices. Let's go ahead and simplify what those 2 squareds are. So
why is it being treated like a logarithm though?
Why is what being treated like a logarithm?
I mean, that's the interesting logarithms though, so how do we find that?
No, there's nothing with logarithms here.
Just wondering, so
Think of it this way, Nick. If I had x cubed times x, or sorry, x squared times x cubed, what would that be?
next spot.
Yeah. You simply added together your exponents. So what we're doing is we're basically going from here backward. I'm adding my exponents, so I rewrote it as multiplying times the bases. Other questions so far? Okay. So again, let's go ahead and find out what those numbers actually are. So we have 4 times 2 to the x minus 1/4 times 2 to the x. Still not one of our options. Let's try factoring out that 2 to the x. And I'm left with 4 minus 1/4. And when we simplify that, we'll just go over here. 4, same thing as 16/4. So 16 minus 1 is 15/4. So 2 to the x times 15/4. Still not up there. But we can see that that's going to eliminate e, because it's not 17 times 2 to the x, and d, because it's not 15 times 2 to the x. And we could even eliminate a, because 2 to the x is not in our denominator. So that leaves us down to that 50-50 shot again. But notice that with each of those, it has an exponent of x minus 2. So let's try to get it in that exponent of x minus 2 and see which one matches up. Also, at this point, you could break this up with division, break that up with division, see which one matches. Up to you. Alright, so again, I want to have an exponent of x minus 2, so let's see if we can rewrite anything as a base of 2. Lo and behold, we can. So then, again, if I have like bases here and I'm dividing, that's the same thing as subtracting our exponents. And now we have our answer B. So I have 2 to the x. If it was 2 to the x, it'd have to be multiplied by 15/4. 17 is not 15/4, and 15 is not 15/4. Does that make sense? Mm-hmm. So if we have 2 to the x, and the only other thing we have left is that coefficient, then we have to be 15/4. Other questions? This piece here? Yeah, so this is the same thing as 2 to the x over 2 squared times 15. And when we are dividing like bases, we subtract exponents. And again, guys, you could have from here said, oh, well, this is just 15 times 2 to the x over 2 squared, which is 15 over 4. So you could have gone backwards. Other questions with that one? Quite a bit more of the algebraic manipulation. Alright, I think is 18 finally our limit one? I'm hoping it is. Yes? Good. Because I want to talk about that one. Alright, so one of our properties with limits is that we can bring the limit into a function as long as it is a continuous function. And we were doing this without even thinking about it. We were doing this without even really thinking about it. If I had the limit as x approaches, I don't know, 9 of 2x minus 5. We said that this is the same thing as 2 times the limit as x approaches 9 of x minus the limit as x approaches 9 of 5. So we would bring that limit into our function, and you can do this as long as your function is continuous. So we also dealt with this, so we would bring up this coefficient. Even if this was x squared, I could rewrite this, say it was the limit as x approaches 9 of 2x quantity squared. This is the same thing as the limit as x approaches 9 of 2x quantity squared. Again, this is a continuous function, so I can bring that limit into it and then square it. E to the x is also a continuous function, so we can apply that same thought here. So that's what's happening here. So they're asking us to find the limit of natural log of y equal to 2. I really need to write on this. Let's see if I can just get it to it.
In my question, there was like, what was like the f x and the g of x, like what are those supposed to mean?
So we're just saying that it's an exponential function. It's a function raised to a function. We don't know exactly what it is, but regardless, we can still use this property for it. Okay. So we are trying to take the limit as x approaches infinity of natural log of y equal to 2. Now, oh, that was part of the question, right? Please say this part of the question. Yeah. So we're trying to find out what is natural log of y equal. All right, well, I need to get this to be just y. So if I exponentiate both sides, then I end up with e to the limit as x approaches infinity natural log of y, which is, as we see over here, I can take the limit in and out because exponentials are continuous. And exponentiating the other side, we get e squared. So from going from this step to this step, we're just exponentiating both sides. We're taking e of both sides. Questions on going from here to here. And again, I can take that limit out because e is a continuous function. Then from there, e and natural log reduce, so we have the limit as x approaches infinity of y is just e squared, which is our answer C there. So I require you to go back to your properties of limits. And again, the limit can enter in and come out of a function as long as it is a continuous function. Most often we see this in bringing up that coefficient or breaking apart across adding and subtracting. We've done a little bit where we had also, you can bring it inside of power, but again, this is true for any time your function's continuous. You can take it in and out of different pieces. All right, questions with 18. Okay. All right, so we'll pause with that, and if we have time, we'll come back to 8 and 6. If you had 8 or 6, and we don't get to, make sure you come see me so we can go over it. Okay, so today we are doing inverse trig, as you can see on your assignment sheet. Oh no, it's not that. Let's focus. Turn and talk to those around you and make sure everyone's awake. I'm going to stick mixed files here since they're set together.
Yeah, okay, there's like one that's bigger one. It's like the middle and then the side. Like a big one. You notice the big wall section and then there's like two. We got the two. Everyone in the middle was square. The size is still good. Like it's not even close to the screen either. So it'll just be right there. Just need to bring the glasses.
Is there anyone that did not get the notes?
I'm just like this whole time.
I try to like move up like really close.
I hate when I forget my glasses. Because the movie's so much fun.
Okay. So today we are doing inverse trig. We're going to take a look at the derivatives of it as well as integration dealing with it. Now with inverse trig, we are focusing mainly just on inverse sine, inverse cosine, and inverse tangent. What's another way that I could say or write inverse sine? Good, arc sine. So just keep in mind arc sine, arc cosine, arc tangent. Okay, so here we have our derivatives. The derivative of arc sine is 1 over the square root of 1 minus u squared du dx. So this is written with u substitution, sorry, not u substitution, with chain rule applied here. So this piece is just following the chain rule if u is something more than x. Okay, so just make yourself a note, chain rule applies. It applies to all of our derivatives. Inverse trig is no different. So if you have something more than just x, you have to multiply by the derivative of that. Alright, what do you notice is the difference between the derivative of arc sine and arc cosine? Yeah, there's a square root for arc cosine. And then for tangent, we see a couple differences here. There's no square root and it's a plus sign in between. Okay. Now, these are 3 derivatives that you do want to commit to memory, just like you needed to commit to memory that the derivative natural log of x is whenever x good. And the derivative of tangent is secant squared, and the derivative of cotangent negative cosine squared. Okay, so these 3 you do need to commit to memory, but if you happen to forget them, you can quickly derive it off to the side. So I will do one for you. What would you like? Inverse sine, inverse cosine, or inverse tangent? Raise your hand for sine. Cosine? Tangent? Everyone always wants. Alright. So we'll go ahead and do inverse tangent here. It's the same idea, same process for each one, just it's starting out with a different function. Okay. So let's let y be our function here. And we'll just stick with the normal x there. Okay, so if I were to do my derivative, I should get this. That's what we're aiming for. But we're pretending that we don't know it here. So we've got to rewrite this before I can actually do my derivative. Alright, so I don't know the derivative of inverse tangent. How can I get rid of that inverse tangent? What is the inverse operation of arctangent? Tangent. So tangent and inverse tangent are inverses. They undo each other. So if I take the tangent of both sides, I can rewrite this as tangent y. Tangent of inverse tangent cancel each other out equals x. Are we okay with that? We're really just converting it to original tangent. But again, the long process is that if I take the tangent of both sides, tangent of y and tangent of the right side. Those cancel and leave us with just x. Just like square root and squared undo each other because they're inverse operations, tangent and arctan undo each other. They're inverse
You need
operations.
to look like select piece on the x or not.
Not necessarily, since that's the only piece there. Okay. Are we okay for me to move on from here? Okay, we made it. That's the hardest part. Alright, so now I'm going to do my derivative, and I'm going to have to do it implicitly, because now it's no longer an explicit function, but an implicit. So what's the derivative tangent? Secant squared y, and then we're going to dy dx, because we're doing it implicitly. And the derivative of x? 1. So when I solve for dy dx, which is the same thing as our derivative, I get 1 over secant squared of y. Now, obviously, that's not what we see here. This is in terms of y. Let's get it in terms of our x. What is 1 over secant squared y equivalent to? Cosine squared, yeah. Okay, so if we could just figure out what cosine squared of y is, then we'd have our answer. Well, let's take a look and see. Let's set up the triangle that satisfies this situation. Alright, so I'm trying to find, actually we're going to go back up to here. It's supposed to satisfy this equation, which means it should satisfy this. So tangent of y equals x. Y is my angle that I'm looking at. You can pick whichever angle you want. I'm just going to go with this guy here. Alright, so tangent, if I were to do tangent of y, what sides am I working with? Good, opposite over adjacent. So if tangent of y equals x, would you guys agree that's the same thing as x over 1? Alright, so this is my opposite, and this is my adjacent. Okay, so opposite would be x, adjacent would be 1. Okay, so now let's try finding what cosine of y is. What's the problem here when I try to do cosine of y? We don't know our hypotenuse. But how do we find our hypotenuse? Pythagorean theorem. Thank you, geometry teacher, for teaching me the Pythagorean theorem. I'm so glad you did. Alright, so when I do this, I have 1 squared plus x squared equals that guy. So when I solve for question mark, what do I get? The square root of x squared plus 1. I'm going to go ahead and keep it as 1 plus x squared, though, just so it looks similar to that. Are we all okay with how we got that? Okay. So now I can do cosine. You know, let's go up a little bit here. Cosine squared of y is just cosine of y quantity squared. Okay. So now when I take a look at my triangle, what is cosine of y?
1 over x squared.
1 over square root of 1 plus x squared. And that all gets squared. Are we good with that? Okay, so now square the top, square the bottom. 1 squared is 1. Square root of 1 plus x squared, that whole quantity squared, just 1 plus x squared. So our derivative is 1 over 1 plus x squared, as we can see represented here. So if you get to a test and you're like, oh my goodness, I do not remember my inverse trig, derive it. Like, you got it. No problems there. Now, I will say that inverse trig is not as common as regular trig. So you won't see it as often, but it is guaranteed still going to be on the AP exam in some shape or form. Questions with that? Okay, so again, same idea for sine and cosine in that you would want to first rewrite it. So take the derivative implicitly, build your triangle, and then you can have your derivative. Okay. So let's go take a look at just doing some basic derivatives with these. Now chain rule still applies, product rule still applies, quotient rule, power rule, all that still the same derivative rules, just now a new set of functions. So let's take a look at this first one here. Alright, so my derivative is for sine 1 over the square root of 1 minus u is my argument. My argument here is for x. quantity squared. And then what else do I have to do? Multiply by derivative of my argument and derive 4x. It's just 4. For response, you can leave it like that. Let's clean up just a little bit though. So I would have 4 over square root of 1 minus 16x squared. There's our derivative. Questions on that? The key thing, don't forget your derivative. Alright, let's go and take a look at number 2. So the derivative of tangent, derivative of arctangent is 1 over 1 plus my argument squared, which is x cubed, times derivative of my argument, 3x squared. Once again, let's clean it up a little bit. So I have 3x squared over 1 plus x to the, is it 5th or is it 6th? Ooh, I keep getting conflicting answers. To the 6th. Exponent raised to an exponent, we multiply. So that's my derivative. Can I reduce 3x squared with x to the 6th? No. Can I, over here in my blue, say that this is just 4 over 1 minus 4x? The square root of 1 minus 16x squared is just 1 minus 4x. No, we cannot break up a square root over plus or minus. Okay, go ahead and give number 3 a try. We aren't going too crazy here, just doing a few basic derivatives, see how you do with that. All right, check with your shoulder partner, see if you got the same thing. All right, did we get this? Did we agree? Good. Stephen agrees. Does anyone else agree? All right. Questions on that before we try another one that's a little more complicated? Okay. I'm thinking 4 should be next. Yeah, let's go with 4. What do I have to use with number 4? Product rule. All right. So let's carefully do our product rule. Second stays times derivative of the first plus first stays times derivative of the second, which is 1 over square root of 1 plus minus x squared. Derivative x is just 1, so we don't really need that piece. Am I done? Don't forget that last term there. So derivative of this guy. It's the same thing as that to the 1/2, so bring down my 1/2. Inside stays. Reduce the power by 1. Then what? The derivative of the inside, even though you do chain rule so many times, didn't you? Alright, let's see if it'll let me zoom in for you guys. Alright, questions on any piece of that? Yes, sir. Negative 1/2. Exponent to the negative 1. I'm sorry, what did you say? Yeah. Inverse sine of x times 1 plus x times 1 over the square root of 1 minus x squared plus 1/2 times the quantity 1 minus x squared raised to the negative 1/2 times negative 2x. Other questions so far? What do you need with me? That thing's just so tempting for you, isn't it? All right, let's go ahead and simplify it, clean it up a little bit. We'll see. So I have inverse sine. All right, this doesn't really simplify too much. We can write it as one fraction. Anything simplify for this piece? What can we reduce? Yeah, the 1/2 and the -2. Now don't lose that negative. Let's see, we've got, this goes in the denominator, and my negative x stays on top. That goes in my denominator. Alright, can we do anything more now? Kind of went downhill, didn't it? Can I reduce anything? We can do what? Cancel out the funky looking things. Isn't this just square root in the denominator here? I could rewrite that. That's just square root of 1 minus x squared. Then aren't these just opposites? One's a positive, one's a negative. Oh my goodness, can you believe it? That crazy looking thing, its derivative is really just inverse. Now notice we started off with a pretty complicated function here, but its derivative was just a simple inverse sine. Alright, questions with that? Alright, let's do 5 and we'll take a look at our intervals. Alright, so number 5 here, what rule am I going to have to use? Chain rule and our power rule, right? Notice that this is inside our quantity cubed. So when I go to do my derivative, I have to first bring down my 3. Inside stays the same. Reduce the power by 1. Multiply by derivative of the inside. And what is... Stephen, that sounded like the proper mumble. What did you say?
-1 over the square root of 1 minus x squared.
Good. 1 minus, and notice my argument is more than just x. So that entire thing. But since that was more than x, now what do I have to multiply by? The derivative of that. What's the derivative of x over 2? Just a good old-fashioned 1/2. Okay, so again, because this was inside of the power, we had to bring down our power. That's the 3. Inside stayed the same, reduce the power by 1, then multiply by derivative of the inside. So this is just the derivative of the inside. Questions on that? Yes, Thinking it over. While you're thinking over, I'm going to clean it up a little bit. Alright, so it doesn't clean super nicely, but we know we've got a fraction. Let's see, 3's on top. It's a -3 on top. And that cosine inverse of x over 2 squared's on top. Our 2's in the denominator, and square root of 1 minus x squared over 2. Cleans up a little bit. Alright, questions with that? Yes, Alan.
Can you leave it as x over 2 and x over 3?
Can you leave it as what? Oh, can you leave those? Yeah, because what we're doing is this is a fraction inside of my trig there. So that's fine. You don't have to worry about it being considered a complex fraction. Also, if I'm going to be honest with you, this type of problem would not be on free response. It would be more than it would, yeah, it would be fine. But again, you're probably not going to get that. Stephen, was that your question? Alright, other questions with number 5 there? Okay, so let's flip it over to the back side. So again, you need to know these derivatives. And now we're going to practice going backward with them. Because taking the derivative is one way, integrating is taking us back. So we need to be familiar with what these look like to know when to recognize them within an integral. All right. Now we're going to just focus on inverse sine and tangent. Inverse sine, as we saw, the derivative was very similar to our inverse cosine. There's only a difference of that negative there. So when we do our integral, if we have the negative, we can just bring the negative out and then do our inverse sine. The reason is that if you think about cosine is just sine graph shifted a little bit. So there's a property that you learned in pre-calc that deals with that, but we won't worry about that. Okay. Alright, so here we have the antiderivative set up for us. This general rule is pretty nice in that it considers, hey, if this wasn't 1, then what do we do with it? So it considers that fact if we have a constant other than 1 there. Now, we still have to apply u sub as needed, so just make yourself a note. U sub still applies. So be looking for that. Now, again, we know that our bare basics, if we didn't have something more than just x here, and if we didn't have something more than just 1, our bare basics, we said that the derivative of inverse sine is simply 1 over square root of 1 minus x squared. So that's just bare bones, no function inside the function. And likewise, our derivative of arctangent, bare bones, was 1 over 1 plus x squared. Alright, so you can see that if I take my antiderivative of this, I should be getting back to sine. You can see that mimicking the 1 minus x squared. But again, this is taking into consideration, say it was 25 minus x squared, or maybe it was 1 minus 5x quantity squared. So still in that format where it's applied to yourself.
Why does cosine not have it? What about cosine at all?
So that's what I was saying earlier. Cosine and sine are just off by that negative. So if we do have the negative here, you could treat it as inverse cosine, or you could just take the negative out in front and integrate with inverse sine. We will just stick with inverse sine. Okay. So then likewise with our inverse tangent, we can see that this is similar to just our bare basics, and that it's a constant squared plus a function squared. All right. So taking a look at these, just like with natural log, do not force inverse trig. Notice as these are not all inverse trig. So do not force it. We'll take a look at some problems where it looks like it might be inverse trig, but it's actually not. It's going to be something else. Okay, so if I take a look at my first problem here, does that look similar to either of these? Which one? Inverse sine, right? We have square root of 1 minus x squared, square root of something squared minus something squared. So this is just our bare basics. Oh, looking up here. This is just inverse sine of x. And don't forget your plus c. Okay, so notice we didn't need to use a u sub because it was just x squared, nothing more than x squared. So likewise with number 3, what does number 3 look like it would be? Our inverse tangent. Again, we have just a simple 1 and a simple x squared like our original. So this is inverse tangent of just simple x plus c. Now what changes with number 2 as opposed to number 1? Yeah, we've got some a value that's other than just 1. So notice we have 4 here rather than 1, which is fine. Again, our formula here takes into consideration if we had something other than 1. Again, I don't have to worry about u sub because that is just x squared, not a function squared. All right, so let's take a look at this. What is my a value going to be then? 2. Good job catching it. Is 2, not 4. Sometimes I like to rewrite these where it's 2 quantity squared minus x quantity squared, just so you can see it in the quantity squareds. You don't have to. But, all right, so we can now go ahead, since we don't need to do u sub, apply our rule here. Is this going to match inverse sine or inverse tangent? Inverse sine. So I have this is inverse sine of u over a, so my argument, which is just x, over my a value. Let's see. Alright, questions on that? It's really not too bad. Now let's take a look at a little more complicated with number 4. We've got more than just a 1 and more than just an x. Okay. With number 4, does it look similar to our inverse sine or inverse tangent or neither? Alright, inverse sine, good. So let's go ahead and identify our a value and our u value. What is my a value going to be? Root 5. Now what is my u going to be? What did you say, Steve? Not quite. Because we need quantity squared. Root 2 x. Good. So again, if I were to rewrite this, I need this to be a perfect square. So root 5, or sorry, not perfect square. Root 5 squared gives me 5. And root 2 times x, quantity squared, would give me 2x squared. Are we okay with that? I don't like that it looks like 2x. X is not underneath square, so you could even write as x root 2 if you wanted to. Okay, so now we see, oh, we do have a use of something more than x there. So now we just do it like a normal use of from here on out. Alright, so I defined my u, so what's du going to be? Root 2 dx. Do I have root 2 represented up here? Nope, so let's go and divide that over. 1 over root 2 du equals dx. Don't worry about rationalizing. You don't have to rationalize for AB. Alright, so now let's go ahead and rewrite this integral. Dx is 1 over root 2 du, so I'm going to bring that 1 over root 2 in front. And down here I've got the square root of a squared minus u squared. So again, I'm just really replacing this guy with a and this with u. Are we good so far? Questions on that? Okay, so again, just doing our normal use of, and now it's in that format that we can integrate. You guys said it looks like inverse sine. So we have our constant hanging out in the front. The antiderivative of this is again inverse sine of u over a plus c. Now we've got to take our u and a and put it back in. Before we do that, questions on our antiderivative? Okay, so let's go ahead and put everything back in. For lack of space, I'm going to go ahead and go back here. Alright, so u over a, root 2 over root 5 times x. I don't really need that bracket there, but that's okay. Questions on that? So again, not bad. If it's not already in that nice format, identify what your a is, identify what your u is, and rewrite it using those. So now it's in that nice inverse sine derivative form. Okay. Let's talk about how 5 is different from 4. What change do you see there?
There's an x in the numerator.
There is an x in the numerator, that pesky little thing.
And when you don't do the derivative, there's no more.
That's right. Very good, Nick. So
You have to reverse u.
if I were to do like example 4 here, where I let u equal root 2x, du is root 2 dx. I don't have x represented there. So this is going to be an indication that probably it's not going to be inverse trig. We might need to try something else. What else could we possibly use? Well, What would you say back there, Steven?
So,
U sub? Should we go back to our old-fashioned U subs? Where we let the entire thing underneath be my U? Because again, it's a function inside a function, inside another function. Let's take a look at that and see. If I let U be 5 minus 2x squared, what's the derivative of that?
Negative 4.
Negative 4x. Oh, look! There is an x represented there. So that's going to help us to know U sub is probably our winner. So let's let U be 5 minus 2x quantity squared. Du is negative 4x dx. And again, I don't have that negative 4, so let's go and divide it over. Negative 1/4 du equals x dx. Alright, questions on what I've done? Again, we're just going back to when we were first doing U sub. We looked to see what was the inside of the function and was its derivative represented there. Now again, the reason why I needed to try that instead of inverse trig is because in doing inverse trig, I could not get rid of that x dx somehow. Whereas in doing just good old-fashioned U sub, we have that x dx figure. Alright, so now let's go ahead and rewrite this. X dx is simply negative 1/4 du. And then we said square root. This whole thing was just simply u. How do I integrate that? Is that natural law? No. Good. How can I rewrite that integral? U to the negative 1. Integral of u to the negative 1/2, and perhaps now it's a little bit easier for you guys to integrate. All right, what's my well? Let's do it use the pen. Alright, my antiderivative increased your exponent by 1, so it's now positive 1/2, and divide by your new exponent, so dividing by 1/2, the same thing as multiplying by the reciprocal, which would be 2. And if I go and put my u back in, let's see, 2 and negative 1/4 reduce. U was 5 minus 2x squared. Trace the 1. Let's see. Again, you could rewrite that as a radical. Alright, so again, a problem in which at first glance you might think inverse trig, but if you were to try inverse trig, you wouldn't be able to get rid of this x up here, and that would indicate to you to try something else. U sub is often a good option. Question? Steve?
why don't the 2 and the negative 1 simplify down to negative?
Okay. Other questions? Okay. So let's take a look at some other ones. 6. What do you guys think for that? Does that look like inverse sine? Does it look like inverse tangent? Or do we need to do something else? Talk with your shoulder partner real quick. Which one do you think we can use? Inverse sine, inverse tangent, or something else?
That's what I think. No, really good one.
Alright, raise your hand if you said inverse sine. Raise your hand if you said inverse tan. Raise your hand if you said something else. Alright, so if I try inverse tangent, remember for inverse tangent we know that 1 over a squared plus u squared du is 1 over a inverse tangent of u over a plus c. Right? Is that what it says at the top of your paper? Oh, boy, that's... Okay, so if we were to try to use inverse tangent, what would my a be? 2. Good, remember we have to square root that. What would my u be? X minus 1. So then what would du be? 1 dx. Good. Is that represented here? Yeah, so everything's taken care of. We do want to use inverse tangent. Good. So let's go ahead and squeeze this in here. So this is dx, is just du. 4 is the same thing as a squared. X minus 1 was u squared. And so we said that this is, again, our inverse tangent. Now notice with inverse tangent, what's different about it from our inverse sine? Sorry, in terms of the actual anti-curve. Good, the 1 over 8. So don't forget your 1 over 8. Do not forget this guy. All right, so I have 1 over a inverse tangent of u over a plus c. And then we simply need to fill in the actual values. So 1 over 2 inverse tangent of x minus 1 over 2 plus c. All right, questions on that? Where are you stuck? Are you good with identifying a and u? Okay, so my inverse tangent has 1 over a squared plus u squared. I see that 4 is a perfect square, and this is a perfect square. That's what gives us a hint to tangent. Well, remember, it's something squared, so what squared gives me 4? And that's why we chose a as squared. Oh, the tangent part of it. Oh, I see. So this was a squared, and this was u squared. Does that make more sense? Other questions on number 6? All right, so let's take a look at number 7. Does this look like inverse sine? No, there's no square root, no inverse sine. Does it look like inverse tangent? Perhaps inverse tangent. If we were to rewrite this, that looks a little bit more like it in that we have 4 plus x squared, but we have an x plus 2 on top. Okay, so if I just did inverse tangent, my u would just be x, the derivative of that's just dx, so that doesn't take care of the numerator. Okay, so inverse tangent won't help us out. What if I tried u sub, and I let u be x squared plus 4? What's the derivative of that? 2x dx, and I again can't get rid of that. Stephen? Ooh, good question.
Problem is that's not
So, if this was x squared minus 4, we could factor it, but x squared plus 4, we can't factor it. But I like that you thought that, because factoring's a possibility as well.
That's a little bit off for me.
All right, so then what can we do? Steven? We could complete the square. We won't go down that road just yet. Can't factor it. I'll give you a hint. We learned this back when we first learned polynomial integration. You do what? What was that? We split it up. X over x squared plus 4 dx. 2 over x squared plus 4 dx. I can break up the numerator divided by each piece there. So I can break up the numerator over denominator. I cannot break up the denominator. So each piece, the numerator is getting divided by the entire denominator.
Oh wait, should it be a minus
Now, let's say it was like 5 over x squared plus 4. There's nothing you can do. Plus 5 is being divided by x squared plus 4. You can't break that up. See that? Okay. So if I take a look at this now, on my left side, is that going to be inverse sine, inverse tangent, or u sub, or something on top of your shoulder partner?
First one's
Alright, bring it back up front. What do we think for this? Steven? It is U sub. U sub is our winner. Why? Why is U sub our winner for this? Nick?
Because we like do the so we just only have one value.
Good. When I do the derivative of the denominator, we get 2x and x is represented there. Okay, how about on the right side? What's that going to be? Inverse tangent, yeah. I can bring this 2, say not in front, and then I don't have any variables I have to get rid of. Alright. Let's go ahead and finish off this problem here. Alright, focus back up front, please. So let's start off with the left side. You guys said U sum, so what should we let U be? X squared plus 4. So du is 2x dx. And I need that 1/2 du. Run out of space here. Alright. So now when I rewrite this integral, x dx is just 1/2 du. And x squared plus 4 is just 2. Alright, and then let's go ahead and do something over here on the right side. Alright, I'm going to rewrite this with that 2 in front. Over, and let's write that as 4 plus x squared. Okay, so for this blue piece here, what's my antiderivative of that? It's still here. Yeah, natural log of the absolute value of u. Now, technically, we have that plus c. You've got natural logs to get any better, but they come in with our inverse trig as well. Alright, now for the red here, let's go and identify our a value and then go from there.
So the u in red and the u in blue are different?
Correct. I'm actually not going to even do a u sub over here in the red. What's my a value for the red? And since it's nothing more than just x, I don't need to change that to u. It would be the same thing. We just keep rewriting it. Alright, so you guys said this was inverse tangent, right? Yeah. Don't forget your coefficient. The antiderivative of inverse tangent is 1 over a inverse tangent of argument over a. Questions on what I did there in red? Oh my goodness, yes, I didn't write that in, thank you. You saved us, thank you. That was dangerous. Questions so far? Now, why do I have a 1/2 here again? It's the 1 over a. Where did this 2 come from? That coefficient there. Okay, so now let's compile it all together for our final answer. So I have 1/2. What was my u? X squared plus 4. Do I technically need my absolute values here? Not really, since this is always positive. I'm just going to leave it. Better safe than sorry. Alright, and then my 2 and 1/2 reduce. So I have inverse tangent of x over 2 plus c. Why could I just write 1 plus c? Yeah, constant plus a constant, just another constant. Technically, I should say c sub 1, c sub 2, c sub 3. Wow. Okay, questions with that? Alright. I want you guys to take a look at 12. Oh, no, I take back. I'm sorry. We need to look at number 10. Alright, Alright guys, so with number 10 we have a couple of issues here. It has that square root, so that might make you think, what inverse trig? Inverse sine. Now, we see though that we have this t sitting up on top, which makes you think, uh-oh, maybe it's u sub. But if I let u be this piece here, what's the derivative of 1 minus t to the fourth? Negative 4t cubed. Do I have t cubed up there? Ooh. Is t to the fourth the perfect square?
The problem we have though is that there's t on the top of it.
Yes.
I like that answer. Yeah.
Yeah, I mean, well,
How could I rewrite to the fourth as something squared?
two.
T squared, right? So this is like t over square root of 1 squared minus t squared squared. Does that make sense?
I know, but the problem is it's t on the top. Oh,
Are we okay with this? So what would my a value be? What would my u be? T squared. And so when I go to do, because it's u sub within my possible inverse trig, when I go to do my derivative, what's the derivative there? 2 t dt. Oh, look! T dt. So don't automatically assume that just because there's a variable on top, that automatically means u sub. For this particular one, when I choose my u for my inside piece of that inverse trig, it ends up its derivative is represented. Now, once again, if you would have tried u sub, you would have gotten stuck because you would have had t cubed. You don't have no t cubed. All right. So now, well, we need that to be a 1. Alright, so now we can rewrite this. T dt is 1/2 du over a squared minus u squared. And you guys said this is inverse sine or inverse tangent? Inverse sine. Okay, so my coefficient antiderivative is inverse sine. U over a, and u is t squared. A is 1. Let's just write that as t squared. Plus. Didn't really need those brackets, but that's right. Questions with that? Right. So with number 11, what's different?
We have
We have bounds. Number 12. What do you think for this?
well, the problem is we need to use something like for the derivative to get 8x.
For number 12?
Number 11.
Sorry, number 12. For number 12, what are your guys' thoughts? It looks like an inverse tangent, right? But what's my u going to be? Cosine, and what's the derivative of cosine? Negative sine, which is opposite. Okay, so your homework is to finish the problems on this. Now, I also have for you. I didn't even tell you what it was. I could have said chocolate. It's not, but I could have said chocolate. All right. So next class, listen up. Next class is our review, right? So I went ahead and printed out the fake quizzes for you. We will go over this next class. I highly recommend that you go through, set yourself the timer for it to do that. But your homework is to finish this. I highly recommend fake quiz. So we'll go over this next class. So it's in your best interest to do it so you know what questions to ask. Oh, sorry, I'm using this. Alright, you guys